we were getting into how to calculate a determinant, and it was all derived from the properties of the determinant. One by one was simple. The determinant's just the element itself, the single element in there. For two by two, you had this X formula. It's the main diagonals minus the off diagonals products. 3 by 3, we were starting to get complicated. This complicated thing, this was all derived from the properties. And you get this complicated formula, and somebody came up with a sort of algorithm for doing that. That was expansion by cofactors. We went through that in a previous video, so I'm not going to do that again. There's an optional method for a 3 by 3 instead of expansion by cofactors, and it only works for 3 by 3 and not larger matrices. I think it actually works for a 2 by 2, but it's not worth doing. What you do, say this is your beginning matrix. You take these first two columns and put them off to the right in the same order. And then you're looking at diagonals. 2, 2 minus 4, 6 minus 1, 5, 1, 1, 7. Those are the top left to bottom right diagonals. Then you look at the bottom left to top right diagonals. 5, 2, 1, 7 minus 1, 2, minus 4, 1, 6. You do all that arithmetic. Every time I set a diagonal, you multiply all those guys. And then you add the ones that go from top left to bottom right, those three products, and you'll subtract all three of the other diagonals, or you add them all up and then subtract from the total. You ought to try it, see if you like it better than expansion by cofactors, but it doesn't scale. You can't use it on 4 by 4s. But for larger matrices, the expansion by cofactors does scale. You just keep breaking things down. So here we have a 4 by 4. Remember, determinants only apply to square matrices. And since I see 2 zeros in this top row, that would be where I want to expand by. I want to expand by the top row. You generally like rows or columns with a lot of zeros. Otherwise, you just use the first row or column. But anyway, so the cofactor, the 1, 2 term, 1 minus 2, 3, etc., is going to be a 3 by 3. Then you have to break that down into 2 by 2s. And here you can apply that X formula. I'm not going to go through all this arithmetic. Let's see, and this other one. So the 1, 3 term, cofactor. 1, 2, 3, 5, 1 minus 1. Yeah, there you go. And do this 3 by 3. That breaks down into 2 by 2s. It gets pretty tedious. I said I'm not going to do the arithmetic, but it does scale up. In fact, we could write a formula for the determinant this way. Well, here it is spelled out. You can pick a row or a column. Here's what it is if you come up with these cofactors. So here's the formula. In general, it works on bigger matrices. Here's the formula. Expand by a row or a column. And we'll hold on to these formulas because we'll use them a little later to generalize. You want to keep doing that until you finally break it down into 2 by 2 matrices. That's the one you can apply an easy formula to. But if you had a 5 by 5 matrix, you end up having to calculate 60 2 by 2s. And actually, we leave larger matrices generally to computers. And actually, they're going to use Gaussian elimination. We have like three methods so far. You use Gaussian elimination and properties. Remember that? You get it into triangular form by properties, or you expand by cofactors. Or if it's 3 by 3, you can use that optional method. You got 3 methods to compute a 3 by 3. Um, Generally, students will not have to do bigger than 3x3s. A special case like this guy, you've got a column that it has only one non-zero term. The others are zero. So you'd want to expand by that column, which leaves you're basically just doing a 3x3 way. That's going to complete what I'm going to talk about determinants. I mean, we might use determinants, but that's completes how to calculate a determinant and and how to and all its properties and how to apply them. We'll stop.